All right, we've got quite a glare on the screen today. And the projector is slowly coming on. Okay, so there's good news and there's bad news. The bad news is I still have students who have not taken the exam. 2 students. So I can't return your exams to you yet. But maybe that's also good news. I don't know. So that's kind of good and bad rolled up in one. What's that? For the most part, yes. Nope. Everybody will all find out on Tuesday, probably. So just put it out of your mind. We will continue on with our lecture today. We're starting into now heat engines, refrigerators, heat pumps, and we're exploring in more detail the second law of thermodynamics. So prior to this point, we've been focusing only on the first law aspect of thermodynamic problems, meaning mass balance and energy balance. But starting today, we're going to focus a little bit more on second law and how it affects engineering processes in real life. So as we have this discussion of the second law, you need to think about both of them together. We do go into like talking about perpetual motion machines and devices that maybe look good on paper but can be either disproven by the first or second law. So these two really work in conjunction to determine whether or not an engineering process is real and also sort of set the limitations on engineering processes because there's only so much energy we can get out of a source or there's only so great an efficiency we can ever achieve. So the two in conjunction kind of help us to be better designers and also to understand more about these thermodynamic processes from a very simplistic view. So there's a new homework assignment, and please note that today is Thursday, but this homework is due on Tuesday. It's only 4 problems, and you will find that these problems are a lot easier than what we've been doing up to this point. So hopefully that's a positive for you. Exam 2, by and large, is the hardest exam of the class, with the exception of the final, just because the final is long and intense. But I think you'll like this stuff because it's a lot easier. Not that easy means better, but for some students, they like easy work. I don't know why. They want to get the least for their buck as possible. You may have also noticed, I don't know why nobody brought this to my attention, but the course outline was incorrect. I had spring break on the wrong 2 weeks. So I have made a new course outline. What's that? The wrong 2 lecture periods. No, not 2 weeks. Sorry, Zach, to disappoint you with that news. No, spring break's not two weeks long. The wrong 2 lecture periods, so the wrong week period. I fixed that. Here is a new copy of it. Please also note that the homework, if you're using the little handout that I place online for homework to look up problems and things like that, that has also changed. So if you've previously downloaded it, get the updated version of it. Or, as always, you can write them down when you're in class. So pass these around, take a new copy. This is the schedule that we're following. Hopefully there's no mistakes on this one. I don't know how I looked at that so many times and didn't notice I had spring break in the wrong place, but I noticed when I was planning the next couple of weeks. Okay, so we'll move on into today's topic. And we're going to review briefly the first law of thermodynamics, which we should understand pretty well by now, that all real processes have to follow this first law. And that's simply that the amount of energy coming into system minus the amount of energy leaving the system is equal to the net change in energy of the system. Okay, that's the first law of thermodynamics, which is in more simple terms is just conservation of energy. But satisfying the first law doesn't necessarily guarantee that a process is real and can happen, because the second law dictates the direction of energy transfer or the direction of heat transfer, direction of work, that we have certain processes that although they would satisfy the first law, they would violate the second. So the classic example is a hot cup of coffee in a cold room, that even though this hot cup of coffee somehow harnessing energy from the room and becoming hotter in a room that's at a lower temperature than this cup of coffee doesn't violate the first law, it does violate the second because it tells us that energy has a directional quality to it. Similarly, with an electric resistance heater, if we put electricity through that wire, then the wire gets hot, and that energy is dissipated as heat. But we can't put that same amount of heat into the wire and generate that's the same amount of electricity. There are some materials where you can add heat to them, and they do generate a current, which I will demonstrate later, but it's not 100% efficient. And then stirring a mixture, you can stir this mixture, and by so doing, you add energy to the system, which is manifest in an increase in the temperature of the fluid. But the same can't be said that if you just add heat to the fluid or heat up the fluid, that it's automatically going to make a paddle wheel turn. So thinking about the directional quality of energy is important, because if we only focus on the fundamental principle of conservation of energy, then we'll think that all these things are possible that really can't happen in real life. The internet abounds with these crazy ideas and inventions that people have for somehow getting energy out of nothing or creating more energy than they consume. But they either violate the first or second law, and understanding why that is very important. I have actually, there's a janitor at my child's school who always has these ideas that he wants to tell me of this, great invention that he has, and wants my help designing it, and I have to break the news to him that it violates one or two of those laws. But he's trying, and that's good. He's thinking. Okay. So the second law states, again, that energy has quality and a direction to it. So we have to go from a higher to a lower energy state. That's also dictated by the law of entropy, which we'll talk about later. Higher quality energy has more usable work. So when we talk about a high quality energy, we're talking about electricity, which is a very high quality energy. A low quality energy would be heat, okay, that you can't really get a lot of energy from heat. Unless your only goal is just to heat something up. So the second law helps determine the theoretical limits to how much energy we can get from a system, or can predict the degree of completion for a chemical reaction. So with the second law, we can also look at it from a microscopic viewpoint, and we can know and understand whether or not molecules can combine to form other elements, how much heat they release. We don't do that in this class, but it's also governed by the second law. And both the first and second law have to be satisfied in order for a real process to take place. That seeing a video on YouTube or looking at something on paper is entirely different from it happening in real life. And there's a lot of videos on YouTube, not just like violating the second law, but I don't know if you've ever seen videos where they're like, do this, do this, do this, put this thing in the microwave and then it'll start glowing, right? Or like put your cell phone in the microwave to charge it, or, they have these videos that people fall for, and they don't work, and they, cause problems or ruin your phone or whatever. So always take everything with a grain of salt and be skeptical of things that seem too good to be true, and then apply real engineering rules and laws to those things in order to fully understand whether or not it's real. Okay, so as we begin our discussion of the second law of thermodynamics and useful energy sources, we have to define thermal reservoirs. And a thermal reservoir is just a theoretical body that can either absorb a lot of thermal energy or can emit or release thermal energy. And it does so without undergoing a temperature change itself. So if we think about thermal reservoirs in the environment, that would be like lakes, rivers, streams, geothermal sources from underground, the air. So you can use these thermal reservoirs, which in a certain sense are like free energy, in order to achieve engineering processes. A source is the reservoir that supplies energy. So the temperature of this reservoir is greater than the temperature of the surroundings or the temperature of your system. And then a sink is a reservoir that will absorb excess energy, so the temperature of that reservoir is less than the temperature of your system. And we have to be very careful to use proper management of thermal reservoirs, because yes, we can use lakes and rivers and streams as a sink, but if we're just dumping a lot of energy into these lakes, rivers, and streams, what happens to the wildlife? What happens to the plants and the aquatic animals? if we increase the temperature of their habitat by 5, 10, 15 degrees, that it can cause issues and problems. So we have to manage that properly. Some sources that are commonly used would be like natural sources. We've talked a little bit about lakes, rivers, streams. But there are also other sources like furnaces, boilers. Geothermal energy is natural, but waste heat from other processes is often used as a thermal energy source. So if you have some manufacturing process where you're frying French fries or I don't know, whatever it is, that maybe there's some excess heat involved that you have to emit as steam. Well, that steam does have some usable energy in it. We can possibly use it as a heat source for another process. So even though we can't use it, again, to reheat our French fries or something involved in the process that we're currently doing, which we'll talk about in a minute, we can use it for an extension of the process. And then sinks, lakes, rivers, ground, the ocean, the air, things like that. So do you understand the difference between a source and a sink? Okay, and it's important to make that distinction. The basic distinction is that the source is always going to be warmer than your system and a sink is always going to be cooler than your system because you have to gain heat from the source and reject heat to the sink. Work can always be converted to heat directly and completely. So we can take 100% of the work we put into a system and convert it 100% to heat if that's our desired effect. Okay, so aside from a resistance heater where the purpose is to heat a room, we don't generally want to convert all of our work to heat, but it is possible. However, the reverse is not true. We can't take all the heat in a system and convert it 100% back to a higher quality energy source. We can't convert 100% of that heat back into electricity. We can convert a percentage of it though, and that requires something called a heat engine. And I have a very basic heat engine here. This is actually a thermoelectric converter. So you can either hook it up to a power supply and it will run this little motor, and as it does that, one of these legs gets cooler and one of these legs gets hotter. Alternately, you can put one leg in hot water, one leg in cold water, and there's a little thermoelectric material here. You can kind of see it sandwiched in there, that when there is a temperature difference between the two sides of these plates, a current passes across. So this is, I'm not sure exactly what the material is, but there are many types of material that when you have a temperature difference on either side, they have a current associated with them. So this sometimes takes a few minutes to get started. So we'll just let it sit in there and get going. So this would be considered, so this one is the hot reservoir, this is the cold reservoir, so this would be like our thermal source and then our thermal sink, and in between is a heat engine which will drive that propeller. So properties of a heat engine: they receive heat from a high temperature source, convert part of that heat to work, and then they reject the waste heat to a lower temperature sink. And they operate on a cycle. So even though there's this big like circle that just represents a heat engine, within that heat engine itself are several steady flow engineering devices that operate in a cycle that allow us to get this, this work output. And they usually involve some sort of a working fluid, and the working fluid is what we transfer heat to and from. So this one doesn't have a working fluid, there's a thermoelectric material in it. But when we're looking at standard heat engines, generally we'll have like a boiler and a condenser. So heat is coming into the boiler and leaving from the condenser, and then we have maybe a turbine, and then over here we have like a pump. Okay, so hot water or water is pumped into the boiler, heat is added to the water so that it expands into steam. It goes into this turbine, which has a net work output. Then we have this, this steam coming out of the turbine goes into a condenser, and heat is removed from the steam, and then it's pumped back up to the boiler. So there's some amount of work that has to go into the pump. There's heat coming in to the boiler and heat leaving from the condenser, and then hopefully we get some network output from our system. Yes?
So would that like include a steam train?
Mm-hmm. Yeah. So in a train engine, the steam engine doesn't have a condenser, and it's not a closed system, but like the air is the sink for the steam engine.
So this is like cyclical and doesn't need to be built where those.
Right. So there's many different examples of heat engines. This is just one, and this is the common one that we study, especially if we get into thermodynamics, like the second semester of it. Sometimes it needs a jump start. Come on. There we go. Okay, so by operating on a cycle, we're able to get some network output. And because we have heat coming in from the source, even though we have to put some work into the pump and we're rejecting some to the condenser, we do get a certain amount of work out of the system. And so the efficiency of the system is dependent upon how much network out we get based on the amount of input that we have to put into the system. So steam power plant, this is another picture. I guess I could have just gone to the next slide. So we have energy source coming in from a furnace, or possibly from like a solar hot water heater, whatever it might be. It's just hotter than our system itself. Comes into the boiler. We get a network output from the turbine, and then we have energy rejected to the environment from the condenser. So the work in to the pump and the work out of the turbine we consider to be the net work of the system. So the net work out is equal to the work out minus the work in. So when we look at the heat engine, like on this previous slide, there's no work input to it. That's because it's all rolled up into that net work output term. So we're taking into account the work out of the turbine and the work in from the pump. And then it's also equal to Q in minus Q out from the system. So again, we're applying the conservation of energy in this way, but we're also considering the impact of the second law of thermodynamics as we roll through these problems. So thermal efficiency is the fraction of heat input that is converted to work. So if you remembered from previous lessons, we talked about that efficiency is equal to the desired output over the required input. Well, in this case, our desired output is a net work output, and our required input is this total heat input from the thermal reservoir. So the thermal efficiency of a heat engine will always be less than 100%, because if we look at these values, that we're never going to get Q in equal to work net out. We have to reject some of the waste heat to the thermal reservoir at temperature L. And usually for a heat engine, our efficiency is less than 60%. It's very, very rare that we get something that's even above like 40%. So there are some limitations that are imposed by the second law, and we'll talk about those as we go through our discussion in this chapter. Any of these cyclical devices that we have operating between a high temperature reservoir and a low temperature reservoir, we can use the subscripts now H and L instead of in and out. So QH is the magnitude of heat transfer between the system and the high temperature reservoir at temperature H. So this high temperature reservoir has a temperature of T sub H, and this low temperature reservoir has a temperature of T sub L. So the proper notation, or the common notation that is used in thermodynamics, is to call them QL and QH. And so we can just rewrite our thermal efficiency as work net out over QH, or if we use this relationship here at the bottom where the work net out is equal to Q in minus Q out, which would also be the same as saying QH minus QL, then we can substitute QH minus QL in for work net out and rearrange, and we get 1 minus QL over QH. So calculating the thermal efficiency, we can do it if we know the network output, but we can also do it just if we know the temperature of the heat transfer available from the reservoirs in between or on either side of our heat engine. So let's look at an example of this. So I want you to calculate the thermal efficiency of this particular heat engine, and I want you to do it two ways. I want you to do it first using the work net out, and then also using just QH and QL. So using the equations from the previous slide, figure out the efficiency, and then we'll reveal the proper answer in a minute. All right, do you have those set up? All right, so the thermal efficiency is work net out over Q sub H. So 55 megajoules over 100 megajoules is equal to 0.55, or 55% efficiency. Alternately, we can use 1 minus QL over QH, and we get the exact same answer, which is what we would expect. So if we look at this problem, Q sub H minus Q sub L is equal to the work net out. So 100 minus 45 is equal to 55. It all works and balances out that it's a feasible heat engine. Now, it sometimes seems like, well, we're rejecting, 450 megajoules of heat to this heat sink. Why can't we just use that and put it back in the boiler somehow and get more efficiency out of our heat engine? Well, what would happen if we did that? A couple of things. It would violate the second law of thermodynamics, but let's just look at it. So if we have this heat engine that's operating, we have Q in to the boiler, and then a work net out of the turbine. So into the boiler comes this water, which is heated up and expanded into steam. Then the steam goes through this turbine and spins a blade, and by doing so loses some of its energy, and it is converted into this rotational energy of this turbine shaft, which is then generates electricity using a generator. So we have some work out. Well, let's just imagine we remove the condenser from the process. So what is the condition of the steam as it leaves the turbine? So it comes in as a superheated vapor. What does it leave as? Yeah, usually it's a saturated liquid vapor mixture, mostly vapor. So maybe a quality of 95%. Sometimes it's still superheated steam. Okay, so it comes out of the turbine as steam. We're removing the condenser, remember? So what's going into the pump? Steam. Does a pump usually work very well with steam? No. No, you have a lot of problems with air getting into the system, and it can't pump very efficiently. It's not meant to do that. It's not designed to do that. Okay, let's just say somehow we managed to pump that steam back to the boiler. We've probably ruined our pump, and it requires a significant amount of energy to pump steam versus pumping liquid. So then we put our lower temperature steam and try to add it to the boiler with higher temperature steam. So what's going to happen to the temperature of the steam in the boiler? It's going to reduce, right? So then we keep going through this cycle. If we make it through the cycle, we're getting less and less and less out of our system as the temperature of our steam just has to decrease. Right? We're going to ruin our turbine, we're going to ruin our pump. We have to condense it before we reheat it again. So we can't just remove the condenser and say, okay, we're not going to do a heat rejection process, because that destroys the cycle. It's no longer a cyclical event. It's like maybe it's going to make the rounds a couple of times, but probably it won't even finish once. Okay. So can we transfer that heat then back to the higher temperature reservoir instead? If we have a reservoir at 100 degrees C that is adding heat to our system, expanding that gas, some network output, so in this case, this is another example of a heat engine that's just a piston cylinder device rather than a cyclical boiler and condenser. And we're removing heat from gas at 90 degrees Celsius and reducing the temperature back to this 30 degrees Celsius. Can we reject heat at 30 degrees Celsius and put it into a reservoir at 100 degrees Celsius? So can you transfer heat from a lower temperature to a higher temperature? Does it naturally go that direction? No, we have to reject that heat to a lower temperature. That it's not going to work to try to take heat at 30 degrees Celsius and put it into a reservoir at 100 degrees Celsius. It's not naturally going to just go. You can't go from a lower temperature to higher temperature. So this is a violation of the second law of thermodynamics. It can't be done either. So we have to operate in this cyclical process, and we have to reject our heat to a lower temperature reservoir. We can't not reject the heat, and we can't reject it to a higher temperature. Either of those two is in violation of the second law. So this brings us to our discussion of the Kelvin Planck Statement, which says that it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So in other words, no heat engine can be 100% efficient. You can't just receive heat and produce work from it without somehow rejecting heat to a lower temperature reservoir. So that's Kelvin Planck Statement, which is another way of restating the second law of thermodynamics, in that heat has a directional quality to it. We can't reverse that process. Is there a question? No? Okay. Do you guys understand this? Is it clear, or is it kind of like, what is she even talking about? Okay. So let's do an example of a real process. Heat is transferred to heat engine from a furnace at a rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 50 megawatts, determine the net power output and the thermal efficiency for this heat engine. So these should be really easy problems for you. There's a lot less in it than analyzing steady state devices, but you still have to be very careful about signs and making sure that you're doing things correctly. So how do we solve this problem? Okay, yeah, so we don't know the work net out at this point. We could just do thermal efficiency. So thermal efficiency is 1 minus QL over QH, or 1 minus 50 over 80 megawatts. Okay, so 0.375, or 37.5%. All right, so how do we find work net out? You guys are doing this problem backwards. We could start here, work dot net out is equal to QH minus QL, right? That also works? Okay. Okay, so we can find the efficiency first, we can find this first, whatever. So QH minus QL, it's 80 megawatts minus 50 megawatts is equal to 30 megawatts. So then we can do a test too. We can say, okay, I calculated the efficiency one way. Let me calculate the efficiency using the other equation, that the thermal efficiency is equal to the work net out divided by Q sub H. So we should get 30 megawatts over 80 megawatts. And hopefully we get the same answer that we got before. Yeah, so 0.375. I think that chapter 5 has you guys a little bit scared. Like, it doesn't seem like it should be this easy, right? These problems are easy, which is kind of nice, but don't be lulled into a sense of security, because it gets harder again later. Okay. You don't always have to check. But my recommendation is, if you have extra time on an exam, check, because I see students make really silly mistakes where they flip these two, or do whatever. You might as well check if you've got time, just to make sure you haven't made a mistake, because it can happen, right? And it would be a shame to lose all those points on an easy problem because you flipped something around. Okay. All right, so let's do another one. So this one, why don't you guys work on? And then we'll talk about the answer. And I'll have somebody come demonstrate on the board. That would be great. Okay, so Q sub L is equal to QH minus work out.
QH, we know that it is 700 kilojoules.
Yeah, 700 kilojoules.
And work out is 250.
Yep, work out's 250. I'm just repeating so they can hear it on the recording. All right, Q sub L is 450 kilojoules. All right, so thermal efficiency. Who do you want to choose to figure out the thermal efficiency? So thermal efficiency is equal to work net out over Q sub H. Yes? Okay, so thermal efficiency is 250 kilojoules divided by 700 kilojoules. So 35.7%. Okay, so what if we wanted to solve thermal efficiency another way? Pick someone else to do that problem. So we already did thermal efficiency is work net out over Q sub H, and we found it was 35.7%. We can do thermal efficiency is 1 minus Q sub L over Q sub H, which is 1 minus 450 over 700. Yep, so same answer, 35.7%. Good job, guys. All right, so these problems are pretty easy. It's just a little bit of algebra, moving things around, making sure you understand it properly. The difficulty comes in when you have to put a process or a system to the test and say, okay, is this a real system? Is this a real process? How do I analyze it and make sure that it's actually going to do what it says it does? So we'll talk about that a little bit later. But first, let's talk about heating value, because the heating value is defined as the amount of heat released when a fuel is burned. And we talked about this just very briefly when we did an example earlier in the semester with a gas water heater. So we were comparing an electric water heater versus a gas water heater, and we used the heating value without really understanding it or knowing what it was. But so when a fuel is burned completely in a steady flow process, it has a certain amount of heat that it can release. And usually the units are given in terms of energy per unit mass. So sometimes it's kilojoules per kilogram, sometimes it's BTUs per pound mass, sort of depends on what system we're working in and what heating, the stuff is that we're trying to use. So if it's coal versus natural gas, that a lot of times they give it in tons or they give it in rather than kilograms. And sometimes it's given in terms of an energy per volume, in which case we need to know the density of whatever it is we're working with. So looking at the heating value, if you're given a heating value in a problem, it's very important, first of all, to look at the units of it and don't just simply apply it in the same way every time. If it's energy per unit mass, and making sure that, if they've given it to you in tons, then you have to convert it to kilograms or whatever unit system you're working in. And then also make sure that if it's energy per unit volume, that you also convert that correctly. So let's do an example. A car engine with a power output of 65 horsepower has a thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value of 19,000 BTUs per pound mass. So in other words, when you burn a pound mass of fuel, 19,000 BTUs of energy is released. Okay, so we know the net power output of the car is 65 horsepower, and the thermal efficiency is 24%. So we want to figure out the fuel consumption rate. Okay, so you may notice in some of these problems we've had a work dot net out, so we've had energy in terms of megawatts or kilowatts, and then sometimes we have it in terms of work net out where it's kilojoules. So if we want to know the fuel consumption rate and we have an m dot, then we have to look at what the rate form is. So work dot net out is 65 horsepower, so that's going to be energy per time in an odd unit because it's the English system and they have interesting units. So we're going to have to look at things in terms of the energy total, not per time, in order to be able to figure out what this m dot is. So pound mass per hour. A lot of crazy units in here. This is a good example to do because it can remind you and show you how we need to work with things like that. Okay. So let's first convert into all the same units. So horsepower and BTU are related by the unit of time, but it's kind of a funky conversion rate. So work dot out is equal to 65 horsepower. And we can convert that to BTUs per second. So there's 0.7068 BTUs per second for every 1 horsepower. So this gives us a work dot out of 45.942 BTUs per second. Okay, so this is telling us our work output of the car, or the net, power output of the car. But when we're talking about the heating value of this fuel, is all of that fuel directly converted into a work output? No. So what do we need to figure out, or what do we have that helps us figure out how much of that fuel is actually consumed for that net work output, or that net power output? Okay, we have a thermal efficiency. So with our thermal efficiency, do you think Q dot H is going to be higher or lower than work dot out? It would have to be higher, right? Okay, so thermal efficiency is equal to this work dot out over Q dot H. We can solve for Q dot H is equal to work dot out over the thermal efficiency. So this is going to tell us the rate of energy consumption, or how much energy is coming into the system per time. So this work dot out is 45.942 BTUs per second divided by 0.24 is the thermal efficiency. So we find that we're actually consuming energy at 191.43 BTUs per second. So this fuel consumption is going to be equal to this Q dot H divided by the heating value. Which would give us this m dot. So Q dot H is 191.43 BTUs per second. And our heating value is 19,000 BTUs per pound mass, right? So this gives us 0.010075 pound mass per second. Sorry, that's not clear. 0.10. But we are told to give it in pound mass per hour, so we convert that seconds to hours by multiplying by 3,600, and we get 36.27 pound mass per hour. Okay, so whatever fuel or petrol is being used in this car, in order to drive it, we're burning 36.27 pounds of it per hour. Okay, we could do a whole nother problem where we determine how much of the combustion gases are emitted, so how many pounds of whatever is going into the environment per hour. That's a different problem, but that's a lot. I mean, that seems like a lot of fuel. Okay, so let's do another example with heating value. A steam power plant with a power output of 150 megawatts consumes coal at a rate of 60 tons per hour. So in this case, the fuel consumption is given. If the heating value of the coal is 30,000 kilojoules per kilogram, determine the overall efficiency of this plant. So we know work net out, we know the heating value, and we know the fuel consumption rate, or the m dot, of that coal. Okay, so how do we determine thermal efficiency? What do we need? Okay, QH. So in this case, we don't have QH at all. So we can't do QH over QL. We can't do work out over QH. We need to find QH. Okay, so thermal efficiency is equal to work net out over QH. And in this case, we're given it in the rate form, so work dot net out over Q dot H. So Q dot H is going to be equal to what? How do we find Q dot H? Yep, so your fuel consumption times your heating value. So in this case, we're calling our fuel consumption m dot, so it's the amount of mass per time, multiplied by the heating value. Okay, so it's 60 tons per hour multiplied by the heating value, which is 30,000 kilojoules per kilogram. Okay, so we have some conversions to do, right? How many kilograms are in a ton? A lot. A ton. 1,000 kilograms per ton. So we get rid of tons. And then we want to convert hours to seconds. So 1 hour over 3,600 seconds. And then we end up with our Q dot H is 500 megawatts, or 500,000 kilowatts. But we're operating in megawatts. Okay, so we found Q dot H. We now can calculate the thermal efficiency is equal to this work net out of 150 megawatts divided by 500 megawatts is equal to 0.30, or about 30%. And that's kind of standard. That we have very, very low thermal efficiencies when we're converting heat to electricity. So if you think about all of the processes in our everyday life that require heat to be converted into electricity, think about all of that energy that's being wasted. So what are some processes where we convert heat to energy? What are some examples? Yeah, car engine. Okay, what else? Coal-fired power plants. Yeah. Natural gas power plants. Okay, so every time you plug something in, every time you turn a light on, every time, think about how much coal is being burned, how much natural gas is being burned, how inefficient that process is, right? So in a state where primarily our eggs are all in one basket, and that is not renewable energy sources, we create a lot of pollution. And, you know, this is, of course, tinged by my upbringing in Northern California, but I think everybody can agree that we like to breathe clean air and we like to drink clean water. And there are certain impacts that these processes have. So seeing how inefficient, I mean, is that surprising to you that it would be only a 30% efficient process? Is that about what you thought it would be, or is that a lot lower? It's pretty low, right? These processes are not efficient and they're very dirty. There's no such thing as clean coal. That's just like a thing they say that's not really a thing. So we have to be mindful of that. That there's only, there are limitations to how efficient we can make them. That we cannot be 100% efficient when we're burning fossil fuels. That just will never happen. So we have to be conservation-minded in the other sense, in terms of using less energy. Okay, so turning lights off when you leave, not leaving everything plugged in your house, walking when you would ordinarily maybe want to drive. So it's all important. We're ending a little bit early today because normally I would have reviewed the exam with you, but we don't have that today. So use your time wisely, go on a walk, whatever you want to do. And we'll see you on Tuesday with